Hello, everyone. How's everyone doing? So I have the textbook and WebWorks and also the additional problems that I posted in front of me. So please feel free to ask whatever you want from there. Whatever. I guess I'll just start with some random integrals that aren't so easy. And then if you have particular questions, just let me know. So or maybe we'll start with the basic one. So this is number 5 from the midterm additional problems. Okay, so for this one, this is a definite integral, and you want to integrate a product of functions. One of them is log, and the other is x to the 5. So if you see log, then it's always kind of a good idea to just use integration by parts. So let u equal natural log of x. dv will be the leftover terms. And then du will be 1 over x. And v will be 1 over 6 x to the 6. And now we apply it to the integration by parts formula. So u times v is 1 over 6 x to the 6 natural log of x. And then minus 1 over 6 and x to the 6 divided by x dx. Now, there's something that I didn't really talk about too much. But for definite integrals, you can either just find the antiderivative first, or you can plug in 2 and 1 and then put in 1 and 2 here. It doesn't really make a difference, so I will just find the antiderivative and then plug it in later. So this will be 1 over 6 x to the 6 natural log of x minus. So this will be x to the 5. So it's going to be 1 over 36 x to the 6. And then plug in 2 and 1. So in the end, you'll get 1 over 6, 2 to the 6 natural log of 2 minus 1 over 36, 2 to the 6 minus natural log of 1 is 0, and so it's going to be just negative 1 over 36, 1 to the 6, which is 1. Okay. All right. So any questions? Any other questions? Well, I guess I'll just keep. So you want to integrate one over the square root of e to the x minus 1. Okay, so I actually haven't done all these. So I would first try something like this. There is a square root here, and there's something kind of complicated. It would be really nice if this inside part was something squared, because then it would cancel out with square root. So I'm pretty sure it's going to work, but I'm not 100%. So let's just try it. So t squared is equal to e to the x minus 1. We're going to try. Okay? Then 2t dt, you take the derivative, is equal to the derivative of e to the x is e to the x dx. And so we can solve for e to the x. This is going to be t squared plus 1 is e to the x. So if we move this over, then this is 2t dt divided by e to the x, which is t squared plus 1, equals dx. So sometimes with these u substitutions, you don't need to necessarily look. I mean, not always, but sometimes it works. Okay, so let's see if that does any good. So dx is 2t dt divided by t squared plus 1. And then you have square root of e to the x minus 1, which is t squared. So these cancel, so you end up with just 2 times dt over t squared plus 1. And this, you know, is arctangent. So this is 2 times arctan of t plus c. And then t, if you solve for it, is just the square root of e to the x minus 1 plus c. Okay. So any questions with this? Feel free to try to stump me today if you have your textbook, because I haven't done all these integrals. So some of them do look scary, and it doesn't. Yeah, like number 12 looks a little scary, so we'll see what happens when we get there. So any questions with this? Okay. I guess if you have any questions, then you can always just go back and watch this video at like half speed or 2 times the speed if you don't have time. Anyways, let's move on to number 7. So this is another definite integral. So we want to integrate square root of x squared minus 1 divided by x from 1 to 2. So do we just kind of go for it and start integrating? Well, not really, right? Now we have to be careful about improper integrals. So this one wouldn't be defined if x is 0. This one wouldn't be defined if x is less than 1. Because then yes, x is less than 1. Because then this whole thing would be negative. But luckily, we're integrating from 1 to 2, so there's no issues there. So now we can start integrating. Now, this is an example of something squared minus or plus or minus a number squared, or just number. So when you see something like this, then you could think that trig substitutions could work. I mean, you shouldn't jump straight to it because there might be an easier way to do it. For this one, I don't really see an easy way. So that's that. Warning, do not do this. I know it's tempting. It's very, very tempting to do this, but it's not that easy. I mean, first of all, that's not an equality. Anywho, so something square minus 1 is going to be coming from one of these. Sine square plus cosine square equals 1, or secant square minus 1 equals tangent squared. Well, it looks like something squared minus a number is this one. So you want to use x equals secant for our substitution. So let's do that. So let's let x equal secant secant theta. Then dx is equal to secant theta tangent theta d theta. So then this integral becomes square root of secant squared, minus 1 dx is secant theta tangent theta d theta all over x is secant theta. Now, this should be 1 to 2 for x because it's a definite integral. So if you wanted to change the bounds, you actually can, but it's a little hard because you have to think of when secant is equal to 1 and when secant is equal to 2. I mean, actually, it's not that hard because that's when cosine is equal to 1 and cosine is equal to 1/2. So you kind of know that. But if you are willing to do the triangle thing at the end, then you don't need to figure that out. So either or, maybe we'll do it both. But for now, I'll leave it as x for now. So let's simplify this. So this is going to be tangent squared. And then this is going to cancel out. You get just tangent squared d theta x from 1 to 2. So how to integrate tangent square? Well, that's not that easy unless you convert it into secant square minus 1. So the antiderivative of that is going to be tangent minus theta. And then we plug in x equals 2 and x equals 1, which means we have to convert it back into the x. So secant theta x over 1. Secant is hypotenuse over adjacent. So in our triangle, with theta and this, hypotenuse is x, adjacent side is 1. So this must be x squared minus 1. And tangent is opposite over adjacent. So this is square root of x squared minus 1 minus theta is just arc secant or inverse secant. And then we plug in 2 and 1. And so that's going to be 1 minus arc secant 2 minus 0 minus arc secant of 1. I suppose you could just leave your answer like this, but if you can, you should figure out what these values are. So let's talk about them real quick. Secant is 1 over cosine. Cosine of, let's say, 0 equals 1. And cosine of, well, it's this triangle. That's a 60, 30, 90, because you want the short side to be 1/2. So this will be 60, which is pi over 3 radians, is equal to 1/2. And so arcsecant of 1 is 0, 1 goes to 0, and arcsecant of 2, which is 1 over 1/2, is equal to pi over 3. Okay, now you could have actually just used this when you were doing the substitution first to make it into a definite integral going from 0 to pi over 3. And you'd get the same exact answer. But anyways, so so for the midterm, you could just leave it in this form. But I'll be very proud of you if you can actually do this. I mean, it's not that hard. It's just trigonometry. All right, so any questions? So the next one is x minus 1 over x squared plus 2x dx. So how to start this one? Well, you can. I mean, this is not wrong, and I would even maybe do it. You can split this up into x, and then factor this x and x plus 2 minus 1 over x times x plus 2. Then this cancels, and you have an easy integral here. But here, you still have to use partial fractions. So you're going to have to use partial fractions anyways, so we might as well just use partial fractions to the whole entire thing. So let's do that. So for this one, first of all, the power in the denominator is higher than the power in the numerator, so we don't have to use long division. And then this thing factors as these two terms. Now these are two linear terms, so this fraction will split into a over x and b over x plus 2. And so to figure out these coefficients, just multiply these to this side. So this will be x minus 1 is equal to a times x plus 2 plus b times x. And then we just plug in some numbers, usually the roots, for linear factors. So if x is 0, that means that on this side it's -1. This is equal to 2a, and b is or x is 0, so this term cancels. So a is equal to -1/2, and when x is -2, this is going to be -3 is equal to -2b. And so a is going to be -1/2, and b is going to be 3/2. Okay, so let's just integrate. This is going to be -1/2, 1 over x, plus 3/2, 1 over x plus 2, dx. And so this is -1/2 natural log of x plus 3/2 natural log of x plus 2 plus c. Okay, so you want to sort of be able to just do this. If you see something like 1 over x plus a, this is just natural log of x plus a. It will be different if there's like a square here or a square here or there's a number here. Oh, plus C. But for these partial fractions, you don't really want to be wasting too much time integrating after you do the partial fractions. All right, so that's that one. So feel free to comment anytime. I'm seeing the screen. It's very quiet. Yeah, lots of like buttons, but like you don't need to like it. Just tell me what you're thinking. Or smash that like and subscribe button. There's actually a professor that's a YouTuber in math. And he has like 10,000 or something, or maybe 30,000 subscribers, and he gets like $100 a month for doing math on YouTube, and I get 0. Can you do an example where there are exponents in the denominator? Exponents in the denominator. Something random like this? Huh? All right. So this is, maybe we'll even do this. Yeah. This is like the most general one. So it might take a while. But here goes. So this is irreducible because it has no roots, right? You can't make it 0. This you can make it 0, but there's a square here, so it's a repeated factor. So let me actually make it a little bit more easier on myself and make it 1. So with this, there's no immediate substitution that comes to mind. You wouldn't really want to use trig substitution because then it's kind of hard to deal with the x plus 1 term. So anyways, the splitting goes like this. So this is going to split as ax plus b over x squared plus 1 plus c over x plus 1 plus d over x plus 2. No, 1. But then square. So you have to have as many repeated factors as there are powers. And then if it's irreducible, then this thing up here has to be a linear factor, ax plus b. But how you solve it is still the same, except it's a little bit more tedious. Actually, a lot more tedious. So you multiply this onto this side. So what you end up with is going to be 1 equals ax plus b and x plus 1 square plus c times x squared plus 1 times x plus 1, and d is going to be d times x squared plus 1. Okay, so that's pretty bad, but it's not that bad. So at least we can figure out what d is right away. So if we plug in x equals -1, then we get 1 is equal to, so this is gone and this is gone, but this stays. -1 squared is 1, 1 plus 1 is 2. So d is 1/2. So okay. Now what we have to do is multiply everything out and match the coefficients on the left-hand side, because there's nothing you can plug in right now. Well, so the thing is, you can plug in whatever you want to, and you'll get an equation. And then if you do it 3 times, then we'll have 3 equations and 3 unknowns, A, B, and C. So you can solve for them. But there's no real good values that I can think of. So let me just double check that I did it right. Yes, I did it right. Okay, good. All right, so let's multiply everything out. Oh, geez. Okay. This is ax plus b times x squared plus 2x plus 1 plus c times, if you multiply this out, you get x cubed plus x squared plus x plus 1. Plus 1/2 x squared plus 1/2. And all of this is equal to 1. So now let's multiply this all out. So this is going to be, so ax cubed plus 2ax squared plus ax plus bx squared plus 2bx plus b plus cx cubed plus cx squared plus cx plus c plus 1/2 x squared and plus 1/2. Oh my god. All right. So I think we have some space over here. So if we collect the terms, we're going to get a plus c x cubed plus 2a plus b plus c plus 1/2 x squared plus a plus 2b plus c times x plus b plus c plus 1/2. And that's supposed to equal 1 plus 0x plus 0x squared. Oh, I'm going off screen. So all of this is equal to, so this part's 0, 0, 0, and this is 1. So then our 3 equations and actually 4 equations and 3 unknowns, so it's an overdetermined system, is going to be something like this. So I guess this will have to go. So we're going to get a plus c equals 0, 2a plus b plus c plus 1/2 is equal to 0, and a plus 2b plus c is equal to 0, and b plus c plus 1/2 is equal to 1. And so I think there's actually something wrong. Yeah, I think I messed up somewhere. So I kind of know that I messed up somewhere because if a plus c is equal to 0, that means b is equal to 0. So they're all 0, but that can't be the case. So Ugh. I shouldn't have erased everything. This is terrible. Since we learned so many methods when we determine what we're going to use. Not really. For this one, you pretty much have to do partial fractions. But yeah, maybe I shouldn't have made it so complicated. Okay, so suppose we figured out what each of these things are, and let's say they're all non-zero. So if you did it correctly, you'll get nice numbers. So how do you integrate each type? So then this is going to be, you can split this one up into a, because that's just a number, and then x over x squared plus 1 dx plus b times 1 over x squared plus 1 dx plus c and 1 over x plus 1 dx plus d and x plus 1 squared dx. So this one, you could use u substitution with u equals x squared plus 1, and then you'll end up with a times natural log of x squared plus 1, but then you have to divide by 2 from the 2 here. This one is just going to be b times arctan, plus this one is c times natural log of x plus 1, plus this is just u substitution with x plus 1, and you end up with just negative d over x plus 1. You just use power rule for this one. So for each of those terms, that's how you deal with it, and that's as general as it gets. If you have a repeated irreducible here, then you could potentially have something here with a power. So then you have to use strict substitution. I won't make you do that, but that's how it would be done. Okay? No, not this complicated. Maybe like something like that. Yeah, I wouldn't make you do A, B, C, D. Like at worst, it'll just be C. Okay, well, so I guess if I rewatch the video, I'll probably figure out where I did my algebra wrong. But algebra teacher, I'm a calculus teacher because my algebra skills are not very good. All right, let's move on. Maybe if someone has like a problem from what, move on to number 9. Yeah. Secant to the 6x dx over tangent square x. So we're back in trig, very nice. So this one is secant to the 4th x times secant square x dx over tangent squared. And whenever you have an even power of secant, it's very nice because you can take out a secant squared, and then whatever you have left over is going to be secant to the even power, so you can use the trig identity once more. So this is going to be secant square squared. Secant square is tangent square plus 1. So in all of this is secant squared, but then you square it. But then you get secant to the 4th. And then secant square, and then all over tangent squared. And then the rest is super easy. So now you just do u equals tangent. Du is secant square dx. So you can convert this into just an algebra integral. So this is going to be u squared plus 1 square over u squared. And then secant squared dx is du. And then it's an algebra integral, so now I'm nervous. But this is not too bad, because this is just u to the 4th plus 2u squared plus 1 divided by u squared du. So this is going to be u squared plus 2 plus 1 over u squared du. And so now that's just the easy power rule. This is going to be 1/3 u cubed plus 2u plus minus 1 over u plus c. No, wait. Yeah, plus c. And then u is tangent, so just plug in tangent. One over tangent is cotangent plus c. Okay. So any questions of this? All right, so the next one is this thing. This thing, again, is not too bad because you can either let t equal to something squared to get rid of the square root, or you can just let the whole thing be u, and you get the same exact answer. So what I mean is this. You can either do x equals root t, or you can do t equals x squared. Right? So we're either letting this whole thing be some variable, or we're letting t be something squared. But as you may have noticed, these are the same equations. So if you calculate dx, this will be dt and then 2 root t, right? Or if we do this one, we'll get dt equals 2x dx. So if you divide this over, you have dt over 2x equals dx. But then x is root t. So we can replace this with root t. So actually, you get the same exact substitution. Anyways, so this is going to be, what is it going to be? All right, we don't want to go here. We want to actually go here. So dt is 2x dx. And then root t is x and dx. And now we have to use integration by parts, because it's a product of an algebra function and a trig function. And I don't really see an easy way to do it. So let's try integration by parts. So let's let u equal to x, dv is equal to cosine x dx. So du is dx, and v is sine of x. So all of this is 2 times uv is x sine x minus v du is sine of x dx. And so this is 2x sine x and plus cosine of x, 2 times cosine of x plus c. But then x is root t, so this is 2 times root t sine root t plus 2 times cosine root t plus c. Okay? Are there questions? I want to check my answer. You're looking at it. These are the solutions. You can also check out this website called Symbolab or Wolfram Alpha, or, I mean, in this day and age, there's like a lot of online calculators. So Symbolab. And you can figure out what the answers are for your integrals. And they even show you the step-by-step way to do it. And they even show you like really nice detailed ones if you pay money. And just ask me. All right. So the next one. Could catch you off guard if you aren't paying attention. Because you have a absolute value of x, right? So that's pretty bad. And also this could be an improper integral because the denominator could be 0. Except that's impossible because absolute value of x is always non-negative, and then you're adding 1, so you're just making it bigger. So there is no singularity here. So how to deal with this? So before, how did we deal with absolute values? As you figured out where this is equal to 0, right? So you would maybe consider splitting the integral up like this and then using the relevant sign. So it's either going to be something, let's see, 1 minus x and x 1 plus x. And neither integral is super hard, but you have to use long division, and it's going to be like 2 different long divisions. So it could take a while, but you could do this, and in principle, you can get an answer. But you don't need to do that because if you notice, we're integrating a symmetric interval. So if the function is an odd function, then you're done because it's going to be 0. So an odd function is if you plug in negative, then it's negative of the original function. So if f of x is x over 1 plus absolute value of x, then f of negative x is going to be negative x over 1 plus negative x, which is negative x over 1 plus absolute value of x. So that's just negative f of x. So the negative sign went outside. I should have maybe written it like this. So it's an odd function, so this thing is just 0 because integrating odd function on symmetric interval. Okay. Now, how can I maybe change this problem up to mess with you guys? Because sometimes I do evil things like that. Is I could make this into 4. Then it's no longer a symmetric integral, right? So then do you have to do what I just said where you split up the integral into 2 pieces? Well, not really, because you can split this up. Okay, you have to split this up, but you don't need to split it up into where this is positive and negative. You could just split it up into negative 3 to 3 and 3 to 4. This part is going to be 0, just easy. This is going to be not that bad because, well, it's just one integral. It's from 3 to 4, which means absolute value of x is always positive. So it's this integral, which is not that bad to do. So be on the lookout for things like this. Okay? I warned you, so now you should be warned. I don't know. Maybe I'll do something like this, but maybe not. I mean, I have to give the exams to the calculus coordinator. So if he or she is okay with it, then that means it's like, okay, like I'm not going to put these randomly evil questions without approval of the calculus coordinator. If we split it, we still get 0. Yes, exactly. Yeah, so this will be 0 to 0 because of like the even and odd stuff, but then you just have a leftover thing. So basically it's like you're calculating this integral and you want to calculate all of this. Well, you don't need to calculate this part because they cancel out, so you have to just calculate. I mean, why the unhappiness? Now that you watched it, everyone that watched it is gonna get that question, and the people who are too lazy to not watch this aren't gonna get it. So you're above the curve, right? That's good. Good news. Maybe bad news for your friend who's probably too busy partying right now because it's some sort of holiday, but it wasn't for me. This one. This one is a little bit tricky because it's not so obvious what the substitution should be at first. So, well, a couple of things you could try is like make this whole thing into like maybe even t squared so that you deal with the square root. But then this is bad because you have 3 over 2 x to the 1/2 plus 1 2t dt. And then this is kind of hard to deal with, especially the 3 over 2 here is hard to deal with. So I don't really see a way to do it like this. But what you can do is something like this. So this, it's similar how you substitute in something squared to get out of the square root, but you have basically like a square root inside. So you have to deal with this first. So let's let x equal to t squared. Then dx is equal to 2t dt. Okay. So now have dt. So 2t dt is dx, and then x is t squared plus this is going to be what? T squared and then 3 over 2. So that's t cubed. So you get t cubed here. Okay? So you can factor out a t squared from down here. So you have t dt over square root of t squared 1 plus t. But then when you split the square root, this cancels with this. So you actually just have 2 times dt over square root of 1 plus t. And then we're basically done because, well, I guess not. I thought we did an example of this. Okay, so, but this is not that bad. So this is a lot better for substituting this entire thing as something squared, because when you take the derivative of this thing, it just goes away. And unlike this one, where if you took the derivative of the whole thing here, then you get some constants here. So all the hard work is done. So now let's see what happens. So what the heck is this? Let's let u squared equal 1 plus t. Then 2u du is equal to dt. And so this integral becomes 2 times 2 is 4. dt is u du divided by square root of u squared. And so you get 4, and then u and that cancel, so you just have du. So like magic, we have nothing to integrate. So the answer is 4u plus c, but now we substitute everything back. So what was u? U was 1 root t. No, root 1 plus t. So this is going to be 4 times root 1 plus t plus c. But then t is root x. So our final answer is 4, and then square root of 1 plus root x plus c. Okay? So sometimes You just have to do it piece by piece. And try to make a substitution that makes your life a little bit better and better. So you can't always just want to solve the solution in one go. That's not how life works. You have to solve little bits at a time. And anyways, if you get an answer and it's like too good to be true, you think, right? Because the last integral was just doing nothing. Well, you can always take the derivative of this, and I guarantee you that we will get this. Okay? All right. Okay. We can do a couple more. So this one is an improper integral. 1 to infinity, arctan of x over x squared dx. Can you use natural log for the previous one? I don't think so. Maybe. Usually you would see natural log as like one of your substitution if there's a 1 over x. ln at the end? Huh? What? No. Okay, so yeah, maybe before I do this, I will say this is a common mistake that a lot of people made because it's just wishful thinking. But you'll have something kind of complicated, right? Like blah. Okay, we'll make it like legit. Something like that. So then wishful thinking is it's going to be natural log of x plus x cubed because plus c. Because if you take the derivative, then you get 1 over this. However, you have to make sure to multiply by chain rule. So you have to multiply by the derivative of this, which is going to mess everything up here. So just because it's 1 over something doesn't mean you should use log, ever. Well, not ever, but you should be careful. And I did see that when I taught 2B a while ago. And like, I mean, I don't know. I don't know how much of an honest attempt those answers were. It might be like end of like the 15 minutes and you'd want to write something for partial credit, but that was like 0 partial credit. So, yes. Okay, so anyways, this is an improper integral if you have an infinity. Then, rather than treating infinity as a number, as many people do, I want you to convert this first into this limit form. And then it becomes a matter of integrating this. So whenever you see log or inverse, so arctan, then think integration by parts. And choose the hard thing as your u. You wouldn't choose this as dv because the antiderivative of arctan is a little tricky, although it's possible. So I'm going to suppress the limit symbol for now. This is slightly poor notation, but whatever. So it's going to be u is arctan of x, dv is dx and 1 over x squared, du is 1 over x squared plus 1 dx, and v is equal to negative 1 over x. So that looks right to me. And so this is going to be uv is negative 1 over x arctan of x plus integral 1 over x times x squared plus 1 dx. Okay. So this integral is easy, or not integral. This limit's not that bad. We'll get to it later. We have to integrate this still. So let's for this one, it's going to be partial fractions. So let's split this up. This is going to be a over x plus bx plus c over x squared plus 1. Sometimes you can just look at it for a while and guess it. But this one, can you? I mean, the way you would guess it is you are going to multiply x squared plus 1 here and x here. Or sorry, x squared plus 1, x squared plus 1, and x and x. So maybe 1, and negative 1? Well, let's just do it. So it's going to be 1 equals a times x squared plus 1 plus bx plus c times x. So if you plug in x equals 0, you get that a equals 1. So that's great. So we have 1 is equal to x squared plus 1 plus bx squared plus cx. So it looks like c is 0 and b is negative 1 because, right, there's no x squares, so this and this need to add up to 0. And then there's no x term, so c is equal to 0. So c is 0 and b is negative 1. Yeah, actually, that was kind of obvious from here. Oh, well. So you get 1 and minus x. Okay. I mean, like, what I mean is, how do you go back? You just do this and multiply x and x, right? So then the x squared terms need to cancel and you're left with 1. So anyways, so if we integrate this, then this is going to be natural log of x minus 1/2 natural log of x squared plus 1. So in the end, you get something like this. You would get negative 1 over x, arctan of x, plus natural log of x over square root of x squared plus 1. So here I used the properties of log, that natural log of a minus natural log of b is equal to natural log of a over b, and also r times natural log of a is natural log of a to the r. And then we have to take the limits, right? 1 to b as b goes to infinity. So the first one is you have to use squeeze theorem because arctan is bounded between pi over 2 and negative pi over 2, because the asymptotes of tangents are pi over 2. And then you just divide everything by negative 1 over x. Well, okay, forget the negative. We'll just leave it outside. Oh, no, that's bad notation. But anyways, so this will be negative pi over 2x and 1 over x arctan of x, and then pi over 2x. If we multiplied everything by negative 1 over x, then we need to flip every sign, which I guess is not that big a deal, but whatever. So if you take the limit as x goes to 0, no, the limit as x goes to infinity, then this will go to 0, this will go to 0. So then by squeeze theorem, this term goes to 0 as b goes to infinity. And as b goes to infinity for this term, well, where does this term go? This term will go to 1 by chain rule. No, not chain rule, L'Hopital's rule. Or you could alternatively do this. You can factor out an x square and 1 and 1 over x squared. So then these cancel, so you end up with 1 over root 1 plus 1 over x squared. As x goes to infinity, this goes to 0, so it goes to 1. So then natural log of 1 is 0. So actually, in the infinite limit, all that goes to 0. And then you have minus 1 arctan of 1 plus natural log of 1 over root 2. Arctan of 1 is pi over 4, so in the end you get pi over 4 minus natural log of 1 over root 2. Okay. So yeah, there was a couple of limits involved after the integration, but it wasn't too bad. Let's see. I want to know what if an exponent like 2 over 3 in the numerator, what is the method for web work 9? May I go to the bathroom? Yeah, sure. Or like, you want me to like not do anything when you go to the bathroom? Just watch the video afterwards. Okay, let me finish up one last integral from the additional problems, and then I'll do the web work problem. All right. So how about something like this? All right. Oh, well, my watch is gone. So what to do with this one? So I think this, I haven't actually done all these. Let's see. So for this one, I think it's best if we just let all of this be something squared. And it will work this time because you don't get a weird number coefficient in the front. So yeah, if it doesn't work, we'll try something else. So here it goes. T squared equals 1 plus e to the x. Then 2t dt is e to the x dx. So if you solve for t squared, you get t squared minus 1 equals e to the x. So 2t dt divided by e to the x is t squared minus 1 equals dx. And that looks pretty good. So this is going to be root t squared dx is 2t dt all over t squared minus 1. Yeah, 2t dt, yes, and that is good. All right, so looks like it's going to work. So this is 2 times, this will become t squared over t squared minus 1 dt. So now, because these two things are the same power, you'll have to use polynomial long division, except that in this particular one, I think it's easy enough that you don't really need to. Or maybe even just straightforward trig substitution might work. Although I feel like I might have done that in class and then messed up. So let's just take the safe route. This is 2 times t squared minus 1 plus 1 over t squared minus 1 dt. So this is 2 times 1 plus 1 over t squared minus 1 dt. All right, that's good. So that integral is easy. This integral, you can either do substitution, and you'll end up having to integrate secant, which is, if you know it, then great. If you don't know it, then there's still a way out, which is you can split this into 1 over t minus 1 and t plus 1, and do partial fraction decomposition and integrate that way. I think I will just do trig substitution. That's a plus sign. Oh my god. Oh geez. My t's will be curled this way. My plus signs will be straight. Or I try to do that. Okay, so anyways, let's do this. So we can integrate this. This is going to be 2 and t plus integral of 1 over t squared minus 1 dt. So if we let t equal secant theta, then dt is secant theta tangent theta. Oh, maybe that's a bad idea. This will be secant squared. This will be secant tangent. So you get tangent over secant, which is like sine over. Okay, so it's going to be like integrating cosecant, which again is not that bad, but I would rather do it like this. Going too far off to this way. Okay, so I would rather do something like this. So we know that sine square plus cosine square equals 1. So if we divide everything by sine squared, then we get 1 plus cotangent square is equal to cosecant square. So cosecant square minus 1 is equal to cotangent squared. And then right, so then you can do that. And then the derivative of cosecant is negative cosecant cotangent. And then when you plug everything in, you end up with just secant. And then the antiderivative secant is natural log secant plus tangent. Or maybe if we just do partial fraction decomposition, that's a little easier. I don't know. I mean, they're all kind of the same to me. I prefer the trig way because it's a lot more quicker for me. But yeah, I think trig scares everyone. So I'll just avoid trig and do this. So 1 over t minus 1 t plus 1 is equal to a t minus 1 plus b t plus 1. I think I've done it like so many times I could probably guess it. I think it's 1/2 and negative a half. So let's see if that guess is right. So it's 1/2 t minus 1 plus 1/2 t plus 1. So then if you multiply t plus 1, oh, it should be minus maybe here, and t plus 1, and t minus 1, and t minus 1. Yes. then you'll have 1/2 t minus 1/2 t. So those cancel. Then you have 1/2 plus 1/2, which is 1. So this is going to be 1/2 and negative 1/2. Okay? Am I going too far off this way? So I basically just guessed what the numbers need to be, and then I double checked and figured out what the correct sign was. So you can do that if you do enough of these. Anywho, so if you integrate this, you get 2t plus 1/2 natural log t minus 1 plus, or minus 1/2 natural log t plus 1. What the heck is t? T is that. So all this is 2 times square root of 1 plus e to the x plus 1/2 natural log, my hands hurt, 1 square root of 1 plus e to the x minus 1 minus 1/2 natural log 1 plus e to the x plus 1 plus e. Oof. So we kind of stumbled around this area, but the point was I wanted to show you that there's multiple ways to get from here. Maybe the key point was whenever you see a square root, a technique that I like to use is to let everything here be a square of something. And it doesn't always work, like the x to the 3/2 thing didn't work, but in general, it should work if the derivative that you take after this isn't too bad. And e to the x in the grand scheme of things isn't too bad. Okay, so that was that's not cruel, it's just long. Cruel would be this integral. This one took me a while to do. Anyways, could you go through 17? Oh, okay. Limit as n goes to infinity of cosine square n over n squared. Is that right? No, 2 to the n. So this one is easy case because cosine square is bounded by 0 to 0 and 1, right? Cosine is bounded like that. So then if you divide everything by 0 to the by 2 to the n, then you get this, and then you get cosine square 2 to the n, and this is 1 over 2 to the n. And then as n goes to infinity, this goes to 0. So therefore, by squeeze theorem, this goes to 0. So that's 17. Mr. Teacher, Larry ain't hand me the hamster. I think, oh no, what the heck? Huh. Weird comments. Why the integral of e to negative s is not x, but negative e to the x? Well, that's because the derivative is the same thing, but then by chain rule, you have to multiply by a negative sign. So the integral is that backwards. Let's see, then what was the Webworks one? Webworks number 9. All right. Number 9. From assignment 5. Oh man, okay. Well, here goes nothing. So it's 1/3 to 3 of 7, and then root x over x squared plus x and dx. So this one, I think, should be the same trick. So if you let x be something squared, then something good should happen, but I'm not really guaranteeing anything. So it might work, it might not work. So dx is 2t dt. So all of this is going to be 14, because 2 times 7 is that. And this will be just t. And dx is t dt. All over x squared is t to the 4th. And then x is plus t squared. And the limits here are going to change. So when x is 1/3, t is going to be 1 over root 3. And when x is 3, t is going to be root 3. But we can just back substitute later and deal with it. So let's just keep this as x equals 1/3 and x equals 3. So everything looks good. So let's see. Root t squared becomes t. Dx is t dt and times 2. And then these become that. So now you can factor out t squared. So you have dt and then t squared and t squared plus 1. So it's 14 dt t squared plus 1. So that's arctangent of t. So 14 arctan of t. But t is root x. And so this is going to be 14 arctan of root 3 minus arctan of root 1 over 3. So this, I think that if you just plug this into WebWorks like this, it'll accept the answer. But if you are a pro, then you would do something like this. So you know that tangent of, okay, maybe I'm not such a pro. So this is pi over 6. And this is going to be root 3 over 2 and 1/2. So opposite over adjacent, 1/2 over root 3 over 2. So this is just 1 over root 3. So this is pi over 3. No, 6. And then this will be, it's a complementary angle or supplementary angle, whichever one. So it's this and then 14 times this. So you should plug that in if you're a pro. But if you aren't a pro, then you should just plug that in. You'll get the right answer. So can you also do 16, please? Okay, that one. So the limit as n goes to infinity of cosine n pi over n plus 1. So what the heck is this? Well, cosine is a continuous function. So we just want to take this inside limit. Now, if the limit was something like this, then it's probably not too hard to see that this inside limit is 1. But that's exactly how that works. You can just, pi is a constant. So this goes to 1, so it's pi. So then this is cosine of pi, which is -1. So that's the limit. Okay. And then 15 is just L'Hopital's rule, or you can factor out n squared. 1 is false because you have to, since it's x squared, so you have to do something over x and then something over x squared. 2, if f is continuous and decreasing and the limit is equal to that, then that is convergent, so that is false. Here's the counterexample. 1 to infinity, 1 over x dx. Then this thing is going to 0 as x goes to infinity. However, this is natural log of x minus natural log of 1, and then x goes to infinity, or b goes to infinity, whatever. But this is divergent, so it's not convergent. And 3 is also false. For example, if, let's say, well, I mean, an easy example is, let's say this is f, and let's say this is g, right? Then if you subtract them, then you get negative 1 over x 0 to infinity, which is divergent, not 0. So I think they're all false. 1, 2, and 3. Yeah, they're all false. Okay. Okay, well now, if there are no more questions, I guess that's it. I mean, I'll wait for maybe like 30 more seconds. No more from WebWorks. Okay, well, what? How? How, which one? 10 to do 11. Okay, so 10 and 11? 10 and 11 were on the earlier part of the video. So, oh, on WebWorks. So that one is just the average value theorem, I think. Let me read it a little bit more carefully. Cup of coffee has temperature 95 degrees, where 20 degrees is that. Newton's law of cooling says this. What is the average temperature in Celsius of the coffee during the first half hour? So what is T in? T is in minutes. So then you just integrate 0 to 30 of T. So that's that. The integral, I think, is easy enough that you should probably just do on your own. And then 11. Okay, yeah, 11 looks good. This is a type we haven't done yet. All right, so this one, it's going to be an integration of a rational function, and it will be bad if we're integrating over -5 and -4, but we're not because it's going from -2 to 1, so we can just integrate as is. So now we need to do polynomial long division of this guy, okay? So it's probably easiest if we just multiply everything out. This is x squared plus 9x plus 20. So now we do polynomial long division. We do polynomial long division because the power is higher here. So put what you're dividing inside and what you're dividing by outside. So this is x, and then x cubed plus 9x squared plus 20x, and then subtract. So this will be 9x squared minus 20x minus 1. No, plus 1. And so it'll be minus 9, and then negative 9x squared minus 81. Yeah. X minus, what the heck is this, 180? Yeah, it looks right. So subtract this. So then it's going to be negative 101x, and then plus 181. And that's the remainder. Yeah. So this becomes integrating x minus 9 minus 101x plus 181 all over. So minus sign here and a plus. Right, so it's parentheses. And then x plus 5 and x plus 4 dx. So this is easy. This is easy. This is not as easy. Is there an easy way to do it? I don't really see it. Yeah. So for this one, you have to split this up into a over x plus b, a over x plus 5 and b over x plus 4. Find your coefficients and then integrate. And each of these are going to be log. And then this is a definite integral, so plug those in. So in the interest of time, I will not do that. Let's see, could you do more examples of squeeze theorem? Squeeze theorem. I mean, for squeeze theorem, you basically have, whenever you see a function that's bounded by something, then that's when you should use squeeze theorem. And you don't really know that many functions that are bounded. So sine and cosine are one. Arctan is also another. Arcsine is also another one because it's bounded between negative pi over 2 and pi over 2. Well, no, arcsine won't really make sense because it's not even defined past 1. Like you wouldn't ever ask what arcsine of 2 is because you can't make sine equal to 2. So yeah, arcsine won't really be one. Off the top of my head, that's all I really can think of for a squeeze theorem. I mean, like in a real trivial way, this is, I guess, a bounded function because you're always adding one to like the same thing. But anyways, whenever you see something like this and then something else, then that's when you use squeeze theorem. So you first set up your inequality, and then you multiply across by whatever you're doing. So the limit as n goes to infinity of arctan of n over n, you would evaluate this using squeeze theorem because arctan is bounded by pi over 2. And then divide everything by n. So this is negative pi over 2 n, and arctan of n divided by 2n. And then these guys go to 0 and 0. So it's squeezed between 0. So this goes to 0. And I mean, there's nothing really special about arctan. It could have been sine or cosine or sine square. And you put sine, 1 and negative 1, and then the same logic holds. So that's squeeze theorem. Okay. Okay, well, it looks like there's no other questions. So I guess I will see you guys on Friday. Wednesday, you'll have a substitute. Surprise.